Hi everyone, my name is Abreu de Cristo, and today with the partnership with the Seismic, I'm going to present to you guys the symbolic finite difference computation for least squares reverse time migration. So my presentation has been divided in 6 parts. The first one is the introduction, the second one the theory, third one I'll talk a little bit about the veto, fourth numerical results, conclusions, and the reference. So we know that the currently the most valuable natural resource are the oil and gas, and there are many ways to spot them, and including these many ways, the the indirect tools is the most affordable if possible to infer it. The seismic method is the most one used in the industry to find the oil and the gas trapped on the rocks. And it has been done by using a source which transmits energy throughout the subsurface, and it is recorded on the receivers on the surface. Uh, After we gather this information and create like a shot gather, which is basically the energy uh, recorded on the receivers through the subsurface. So here is it's an imaging that's showing an acquisition, marine acquisition, which is the the ship which is carrying the source and a cable with the receivers along it. So we have here the source which is transmitting energy through the subsurface, which reflect down on the layers, sedimentary rock layers, and everything here, and then goes back to the receivers, and it is recorded on the receivers. Specifically for the marine acquisition, this receiver is called hydrophones. And with this information here, we generate the shot gathers, which shows how the energy through the subsurface behaves. So the theory about my technique lays on the that you can correlate the energy from the source. If you propagate the energy from the source and back propagate the energy recorded from the receiver, and you correlate it, you're gonna get the image of the subsurface. This author here, Basal, talked a little bit about it. And when you correlate and generate the image, we basically have some problems like noise. A specific noise called backscattering noise is a low frequency noise that difficult to see the image properly. So the least square RTM, it's a technique basically to improve this image from the subsurface by using uh, a linear inversion. So we can improve our final image, removing this backscattering noise, and in the end having a better image of the subsurface. So basically here in equation 1 we have the wave equation for density, constant density, and m0 is the is the square slowness, and s is the source. So basically we have this equation, and then we do a perturbation where m is m0 plus delta m. And if we replace on equation 2 this perturbation on the wave field and the squared slowness, we're gonna have equation 3. And in equation 3 we can divide it in two set of equations. The equation here with p0, which is called the background wave field, and a second equation which has the delta P, which is the scatter wave field. With the Born approximation, we can neglect the delta P here in this term. So in the end, we're gonna have minus delta M, the second order partial derivative of P0 in time, with respect to time. So this is equation 5 that we have here, and this is going to be our equation to generate the shot gathers that I talked before. So by using this set of equations here, you're gonna generate the shot gathers. It's clear here that I need to have a velocity model, which is represented here by m0, and then I propagate the wave through this velocity model, and then I will record the data generating the shot gathers. Alright, so this is the forward modeling, but I have to do I have to back propagate the energy from the receivers, which represents the equation 6, and then I can correlate them as I showed on the image. And if I correlate them, I will generate the migration. And as I said, the migration has a lot of artifacts, a lot of problems, a lot of issues. And one purpose of the least square RTM is to remove this kind of noise. The general purpose of least square RTM is to make the image closer to the real image. And to do that, it removes actually the backscattering noise and other stuff. You're gonna see further in some images. So here basically is the algorithm of least square RTM. So you start to update the image iteration by iteration using appropriate step length and the gradient. So for that we use the Vito. The Vito is our open source Python project based on domain specific language, and the Vito uses SymPy to generate its code, and I will show you some examples how we code on the Vito. So basically here I have a piece of code from the Vito, and here I'm defining my P0. Actually is a time function. So here is use my time function, and then I have to define the wave equation here, right? And if I plot this wave equation, I'm gonna have this equation here, you see, which is exactly the wave equation that I showed before. So then I have to discretize my equation to solve it using finite difference. So when I create the stencil, basically I mean discretizing my wave equation, and then I inject the source by using the source inject, which do like an injection of the source, and then I create the rect term, which is the receiver, which will record, which will save the energy from the source after reflecting on the layers. So I'll show now some numerical results. So for this example, I use a velocity model with number of shots of 51. The number of receivers were 431. The grid is 25 by 25. The peak frequency was 15 Hertz. The record length 8 seconds. Sample rate 1 millisecond. The model extension was 10 kilometers by 7 kilometers approximately, and the number of iterations that I used here was 100. So as I said, here we have this is the true velocity model, which in reality we don't have it. We just have the smooth velocity model. It's something close to the real one. So this is that we have. So I use it to perform my least square RTM. Okay, so as you can see, the velocity model here have a lot of interesting structures. This velocity model is super close to a real one. So here you have water layer, here's the sedimentary part of the velocity models, and then this is the salt. This is a stratified salt. This is the base of salt, top of salt here. This is a overhang. This is called a overhang. It's very hard structure to be imaged, and this is the pre-salt. So mainly in the pre-salt that we have the accumulation of oil and gas. So this is the important to image here better. The top of salt and everything will be good to image properly, but the part here on the bottom will be better. But actually, if you image here better, you're going to image here. If you image better on the top, you're gonna be imaging better on below. It's everything is connected. So here's my results. So here I have a true reflectivity, but indeed we do not have it. It's just for quality control. And this is the migration. This is the image generated by using the smooth velocity model. So you see that we have a strong low frequency noise remaining on the image, and we have basically the top of salt. You see the top of salt is not well delineated. The overhang is not clear. The base of salt is super strong. It's not well focused. And after least square RTM, we have a matter image. You see that the top of salt now is close to the real one. The base of salt is better. The overhang is well illuminated. So after least square RTM, you have a image closer to the real one. So this is a very way to QC your results, which means that we are going to the right direction. So this is the misfit function, which shows you that along the iterations it should decrease. Why? Because the shot generated is close to the real one, so you expect it to make to go decrease along the iterations, which is which means that is working properly. The error is decreased. And here I have a very important QC, which shows the reflectivity values, amplitude values. So the black one, dashed black one, is the true reflectivity. It's just for quality control. In the reality, you don't have it, but just for quality control, since it's a synthetic data. And in the blue is the initial one, so you see that it's super. I mean, is super far away from the true reflectivity, the true image. And the red one is the reflectivity after least square RTM, after 100 iterations of least square RTM. So you see that after the inversion, it matches way better than the blue one, and it means that it's working properly. And this is just a well that I extract, like a profile that I extract from the reflectivity on the x equals 7 kilometers, and you see that the algorithm is working properly. My conclusion is that the least square RTM is working properly as we expect. It's improving the image, and the very important thing here is that the Vito produces a very optimized code by using this kind of way of programming, like a symbolic way of programming the wave equations. And about the results, the numerical results, we see that the backscattering noise has gone, the reflectors are more well focused, and the amplitude range of the reflectivity is closer to the real one. And as I said, the base of salt, top of salt, and overhang has been improved as well after the least square RTM. That's it, the reference. I thank you very much. I appreciate your time, and bye bye.